astrO podcast. Welcome to today's episode. And today I have the honor of being joined with Adélie Gorce. I'm sure that's how I pronounce your last name.
Yeah, that's fine.
Okay. She is a cosmologist working from the University of Paris-Saclay, working on the first galaxies in our universe, the Epoch of Reionization, and a new exciting telescope coming in the future. Thank you for joining us today. Could you please give us a brief introduction of yourself?
Hi, Andrea. Thank you for the warm welcome. So as you said, my name is Adélie. So I work in Paris. I've recently been hired as a permanent researcher at the Université Paris-Saclay. And as you very well said, I work on how the first galaxies and the first stars formed in the history of the universe in a field that is called cosmology. That is the study of the universe as a whole, and it's a branch of astrophysics.
And we will be looking more into the new telescope that might be coming in. But before we get started, I'd like to clear the topics that we'll be talking about today, like radio astronomy, where it talks about how the first radio astronomy, where we first got a signal from the first galaxy, that's how we figured it out. And then you might be wondering what the Epoch of Reionization is. It sounds very complex, but actually it's not. It talks about the first galaxies and the first stars that were born in our universe after the Dark Ages, when there was no stars, no light before when our universe first started out. So let's get started with the questions. So my first question is about this new exciting telescope, which is called the Square Kilometre Array, also short for SKA. Now, what is the Square Kilometre Array, and what advancements will it bring to the galaxies and early universe? How will this really help us in our research?
Yeah. So thanks for your question. So the Square Kilometre Array is a telescope that's being built at the moment. The project actually started in the 80s. So the first astronomers to have the idea of this telescope presented it in the 80s, and then it took around 40 years for it to happen. So it's a giant radio telescope. Radio telescopes mean that it targets light in radio, like the one you listen to, for example, when you listen to FM radio, etc. Except that signal that we're targeting is not coming from your local broadcaster, but from the first stars and the first galaxies in the universe. It's being built both in South Africa, actually, and in Australia. That's why we call it a giant radio telescopes. And it's going to be made of about 100,000 antennas that are all put in an array. It's an array of antennas, and the antennas actually look like Christmas trees, as you can see on the picture. And yeah, why is this telescope really exciting? Because it's the first one that will be sensitive enough to reach the faint and distant signal from the first stars that were born in our universe. So that's when the universe was about only 1 billion years old, knowing that today the universe is about 13.7 billion years old. So that's really a really, really long time ago. So that's why I'm so excited about it.
Is it kind of like what the James Webb telescope is doing, that they're receiving light from but from other like distant stars from the somewhat beginning of the universe, and they're also trying to look into 13.8 billion years ago, but I'm pretty sure the Square Kilometre Array will be able to do that way much better. And also, one more thing that I didn't explain in the beginning is that radio astronomy, maybe you've always wondered, how do astronauts talk in space, or how do they contact their mission control or anything, because there's no air in space. Space is a vacuum, so there's no medium that sound can travel through. So radio waves are the only way that they can communicate. So that's one point I would like to address after. So
right.
Now we can go, because you already answered all my questions about the Square Kilometre. So thank you. But let's talk about the Epoch of Reionization, because that sounds really complex. Like, what is epoch? What is reionization? So, first of all, what is Epoch of Reionization in your words? Why do you think it's so interesting for all of us to know about?
So for me, it's really interesting because it's the largest period of time in the history of the universe that we don't know about. We don't know anything about it. We know pretty well the universe when it was really young, when it was about only 300,000 years old, through the study of the cosmic microwave background. We can talk about it if you want. We know pretty well the more recent universe, what we call the local universe, so the one that's surrounding us at the moment, and that is much more, much older. But there's this period of time, the Epoch of Reionization, that probably lasted about 1 billion years. We don't really know, but that we know absolutely nothing about. So it's really the last missing piece in our history of the universe. And if we understand reionization, we'll be able to understand better galaxies, how they form, how they evolve, and maybe also understand better the future of the galaxies that we see today.
Wow. Okay, that's really interesting. I really want to get into that. And what processes occurred during the Epoch of Reionization? Why is it important for us to understand that?
Right. So exactly what happened during the Epoch of Reionization. So to explain that, I will have to go back a little bit in the past, in the history of the universe. So after the Big Bang, the universe is mostly a plasma, which means it's really hot, it's really dense, and it's all the components of atoms that are mixed together, but they cannot form atoms. So that is electrons, neutrons, protons that will later form the nuclei of the atoms. And you also have the photons, which carry light, that are stuck in this plasma. But then as the universe cools down and expands, so expands and then cools down, the temperature goes down, and these particles are able to join to form the first neutral atoms. So that's mostly hydrogen, the most simple atom in the universe, and also a bit of helium and lithium, about the following one in terms of complexity. So after that, most of the universe is neutral, okay, just neutral atoms formed of protons, electrons, and neutrons. But as the first galaxies form, the light that they emit, the radiation they emit, will ionize the neutral atoms. So for those who are not familiar with the ionizing terms, it means that they will kick out the electron from the atom to produce an ion. So that today, when we look at what we call the intergalactic medium, so that is all the matter that is between galaxies, we see that it's mostly ionized. So we try to understand how this transition happened, how we went from mostly neutral to mostly ionized, and if the galaxies were the source of it, what we can learn about these galaxies through this process.
Wow, so there's a lot of particle physics and a lot of chemistry also involved in this. Actually, I'm really interested in chemistry, and I'll be looking really further into chemistry, so I'm really excited to know more about this reionization and epochs. So, what are some main challenges in observing the epoch of reionization, like because these faint signals are very distant from us? So are there any challenges that could occur while observing them?
Yes. So there's a lot of challenges, and that explains why we have not been able to do it so far. We have not been able to do these observations. The first one is that the signal is really far. It's coming from very, very distant galaxies, because as you may know, when we look into the distance, we also look in the past in astronomy. That is because the light has a finite speed. So for example, when we look at the sun, we actually look at the sun how it was 8 minutes ago, because that's how long it takes for the light to travel from the sun. So for these galaxies, we're looking about 12, 13 billion years ago. So it's extremely distant galaxies, and the signal is very, very faint. That's why you need such giant telescope as the SKA, as the one I described before, to observe it. And the other challenge is that, which is somewhat related, is that of course between us and these first galaxies, there's a lot of other objects, a lot of other astrophysical objects of galaxies, black holes, quasars, everything you can think of, even our own galaxy, that emits some other type of light, some radiation that will pollute the observations we have. So out of this bunch of observations that includes the galaxy, galaxies on our galaxy, other galaxies on the way, etc., and the first stars, we need to remove all these elements and only keep the contribution from the first stars, and that's very, very, very difficult.
Yeah. Wow. Actually, yeah, okay. Sorry, I just sorry for a second. But that seems like a lot of work because of all like you said that it might get polluted. Like, what do you mean as in polluted?
Well, it's a bit like when you take a picture. Say you want to take a picture of a flower in the distance, where you might end up picking up all the herbs that are between the flower and you, just because they're on the way. Yeah. So that's exactly what's happening. We're taking that picture, but there's a lot of things in what we call the foregrounds to what we want to look at. And so we just see the sum of everything, and there's nothing we can do about it. It's just there.
And also, I was really interested about how we can actually, like how the James Webb Telescope is doing, how they're looking into time, like back into time, which is really intriguing for me, because I was actually asked a question by my father where he asked that if we looked back to the Earth, like if the James Webb Telescope was all the way back 13.8 billion years and was looking at the Earth, would we see our Earth in the ancient? Would we see it? Would we see the history before, or would we see dinosaurs? And of course, that's not the case. You would just see it when you had first left it. But still, it's a very interesting question to think about. So thank you for introducing that. Now, I wanted to talk a little bit about radio telescopes and how they work to detect signals from the early universe. So how does that quite work with radio signals or radio?
Right. So why we care about radio waves? So the first reason is that it's exactly where the light from the first stars will be. So let me explain. I'll just quickly show a picture because I think I need it. Let me see.
Yes.
Okay. So we look at these radio waves in particular because of the redshift. So as you might be aware, there's different types of light following the electromagnetic spectrum that depend on the wavelength of light, okay? Light is a wave, and the wavelength is the size of this pattern that gets repeated. And different types of light will have different wavelengths. So very short wavelengths, like on the left here, correspond to gamma rays, X-rays that are very energetic types of light. And then as you extend the wavelength, you get to less energetic types of light, like microwaves, radio waves, etc. So that's just how it is with light. But the thing is that in the universe, because of the expansion of the universe, when you have one type of light with a given wavelength that leaves these first stars, then with the expansion of the universe, it expands also the wavelength. So for example, the first stars 13 billion years ago may have emitted light in the UV or in the optical, in the light that we see ourselves. But then because of the expansion, it got extended to radio wave, so that today we see it in the radio wavelength. So that's why we care so much about radio wave in this case. And just a little side note, we call it the redshift, because in the optical, the shorter wavelengths correspond to what we see as blue, and the longer wavelength correspond to what we see as red. And so as we extend, with the expansion of the universe, we extend the wavelength towards redder, quote-unquote, wavelength. So that's why we care about that's why we care about wavelength, radio wavelengths. And the good thing about them as well is that they don't get absorbed by the clouds, which means that you can look at it from Earth, and even if you have a cloudy day, you can still get the signal through. So you're not limited by the weather, which is always
Wow,
good.
I learned something. I didn't know that the waves could be expanded when looking back. So that was very good information to know. So now I know that maybe dark matter, dark energy is maybe not your topic, but that it is related to cosmology. So I just have a few simple questions or a few questions that I have. Is that how does we do know that dark energy is used? We know that dark energy is the reason why our universe is expanding, and we don't know what it is quite yet. So, how are how do dark matter and dark energy influence the large scale structures and evolution of our universe? And what are the current theories about their nature and interaction with other particles and other forces?
Okay, that's an excellent but difficult question. So I would say that they're both an essential part of the model we have right now to explain the universe. So that's called the cosmological model that explains the evolution of the universe from the Big Bang to today. And they're both necessary for it to work. The dark energy on one side explains the accelerated expansion of the universe. So the fact that not only the universe is expanding, but it's expanding quicker and quicker with time. So we're getting further and further away from other galaxies, but also the more time goes by, the quicker we're getting away. So that's what dark energy does. And as for dark matter, it's also an essential ingredient to explain the structure of the universe today. So I can also show. Oops.
Okay.
Sorry. All right. So let me. Whoop. Okay. So in our model of the universe right now, that we call the lambda CDM model, lambda means dark energy. It's the little nickname of dark energy, and CDM means cold dark matter. So in this model, we have about 85%. Sorry, I realized the numbers were gone. Okay, we have a huge majority of the universe that is dark energy, and only a little part of it that is matter. And within this matter, the matter that we know, that we call ordinary matter, so the matter we see around us, that forms the atom as we know them, etc., only represent about 60% of the total matter, and all of the rest is dark matter. And why does it help understand the universe today? Well, it's because I told you at the beginning that the universe was very hot at the beginning and actually very homogeneous. So if we were looking at the universe surrounding us at this time, we would see something like this oval here. So that is just the sphere of the sky around us flattened on a 2D, so that's why it becomes this sort of oval. So it's pretty much homogeneous at the very early times, but when we look at the universe today, it looks a bit more like this. This is what we call the cosmic web, where every little bright point corresponds to a galaxy. Okay, so all these filaments, all this structure is a lot of galaxies grouped together to form this structure, and the darker regions correspond to voids, what we call voids, so regions of much emptier space. So there's something that happened to make the universe go from really homogeneous like this to very, very structured like that. And that's where we think dark matter played a role, because dark matter allowed us to go from this map of the cosmic microwave background that I mentioned before. So this is just a snapshot of how the universe was when it was only 380,000 years old. And it's really tiny, tiny fluctuations. So that's temperature we measure. The average temperature of this map is minus 270 degrees Celsius. So that's very, very tiny. And the little fluctuations that you see, the red points that are the hotter regions and the blue points that are the colder regions, they correspond to 100,000 thousandth variation. So it's really tiny, tiny variations. And you need dark matter to explain that these tiny, tiny, tiny variations actually ended up in making this map of the universe where you have regions of very high density and regions of very low density, like these voids that we see here. So it's an essential ingredient of our model. But the issue is that we really do not understand what it is. Dark energy, there is not a lot of hypothesis at this point, although we're trying to understand it better, and it's a really active field of research. And as for dark matter, we know that it only interacts what we call gravitationally, which means that it only interacts through its mass, basically, just like the Earth rotates around the sun, etc. That's because of gravity. And so it makes it really difficult to observe, because the only way to observe it is through gravitation. So there's a lot of experiments trying to do that. For example, in the big particle colliders, where they're trying to create, for example, dark matter, but so far we haven't managed to. So it's also a really active field of research.
Yes, well, thank you for the diagram and all that. Actually, I've done some research on the cosmic microwave background, and I wasn't aware of this dark energy and dark matter model, so I'm very glad that you introduced it to me. So now that we're running a little bit on time, my final question to you is a little bit on, as you focus on the Epoch of Reionization and the beginning of our universe using this new telescope with the SKA. So why is it crucial for us to understand the past of our universe, and why not about the future that lies ahead? Like, what will happen after all of our galaxies and all the black holes, they all will expand far away from each other, and it just might end up like the dark ages when our universe was all dark. So why is it important to understand this now? And also, how can AI modeling help us in such future scenarios?
Okay. So I think you partially answered your question, because we exactly try to understand what happened in the past to maybe have a better idea of what will happen in the future. So in my case, for example, you try to understand the first galaxies to understand how they evolved, how they led to the galaxies we have today, which will maybe help us also understand what will happen in the future of our galaxy. And as for the future of the universe itself, there's a lot of theories we don't really know at the moment. It is true that if it keeps expanding in an accelerated way like it is doing right now, then we're going to get further and further away from other sources of light, so the universe is going to get darker and darker in a way. But this is on billion of years time scale, so there's nothing to get worried about. And then for the final part of your question, how can AI help us to understand all these things? So we actually use a lot of AI in astronomy, mainly because we have huge data sets. We observe a lot of stars, we observe a lot of huge regions of the sky that produces really big data sets that are really difficult to analyze ourselves. So sometimes we require the help of AI to look through these huge data sets and do some sort of treatment on it, or to classify them, to then us ourselves look at it. So it's really important for this, and it's really helping. So any type of progress made in computing, actually, whether AI or computing or computations in general, CPUs, GPU computation, etc., is really essential to what we're doing and helping us a lot.
Okay, thank you very much for your answer. And I'm really interested to understand more about this topic on cosmology, the expansion of our universe. So here we can end it, but I also like to ask you, do you maybe have any do you have any advice for maybe the young generation on if they're like me who are very interested in astronomy or want to pursue something in astrophysics? Do you have any advice or tips that you'd like to give them on where to start their journey?
Okay. Well, first, if you're interested by all of this, is great, and I think what you're doing at the moment of trying to learn as much as you can from different ways, with podcasts, with books, with online videos, etc. That's really good, because it can help you also pinpoint exactly what you like in astronomy, what you would like to study later. I would say that math and physics are pretty important for astronomy, so that's something you cannot really get out of. But you can go through, you can work in astronomy from really different angles. So you can be a researcher like me, and I do use a lot of computing and math and physics every day. But you can also work from it from another angle. If you work for a spatial agency and you help them send spaceships in the sky to study the universe, you can do a lot of talks like this to explain astronomy to people. So there's really a lot of jobs that are related to astronomy, and it's not limited to a researcher. And so I think, there's a lot of way to scratch that itch for astronomy, and it doesn't have to just be a researcher person. So,
Yes. Well, thank you. I'm also going to use that advice personally, so thank you very much. So, do you have any final questions for me or anything that you'd like to say finally?
Okay. I was wondering what for you would be the next big discovery about the universe that you would like to see happen, or that you are excited about?
So that's actually a really good question. Actually, I'm not very sure if this field is very vast, but I'm very interested in time travel. Not time travel as in we know that if, according to Einstein's theory of relativity, where if the curvature of our space-time bends, we can create like a wormhole and we can travel through different universes. Well, not us time traveling. I actually recently read an article which I was really interested about, was where we can, through the quantum loop, we can send particles back in time. So instead of starting out with humans traveling back in time, I think sending particles back in time would be much more interesting to see how it happened. And there's a lot of analogies that they use on how to describe. There's a lot of quantum entanglement, which is basically when a particle is entangled with another particle, and even if it's light years of distance away from each other, they'll still be connected somehow and will still have some kind of interaction with each other. So because of this, so the analogy that they used was that imagine your best friend is having her party, and she gives you you pick out a birthday gift for her and you give it to her, but then she gives you the what is it called, the wish list that she wants the next day. So what you can do is that you can go back in time, wait for the list. You know the list already, so you give her the gift that she actually wants before she sends the list. But actually, through quantum entanglement, they use some experiment with particles, but they said it's not as reliable because it only happens 1 in 4 times. So we still need to keep doing this experiment to get the reliability. But I'm very excited about this because if we can send a particle back in time, we can change something in history, which can maybe change our present or maybe our future. So I'm very excited about that. Maybe humans time traveling may take billions of years, millions of years, but I'm very excited about this project or this thing that's
This area
happening.
of research. Okay, I
So
understand.
thank you very much for joining us.
Thank you.
I learned so many things today, which I will be using on my astrophysics journey. So thank you so much for inspiring me. I actually did not know much about radio astronomy or the Epoch of Reionization. Thank you for that. So I hope you can join us next time as well. But thank you. It's an honor and pleasure to have you on our show today. So thank you for joining us today on the astrO podcast.
Thank you for the invitation.